Okay, so we can continue the morning session with Nejc Čeplak from local, from Saclay. And he's talking about a singular limit of smooth microstate geometries. So please.
Okay, thank you very much. Can you hear me? Is the microphone okay? Cool. Okay. Yeah, thank you very much for the organizers for organizing this conference. Thank you for also giving me the opportunity to talk. And what I want to talk about today is some work which was going on in this group here in Saclay with a bunch of people who are also in the audience, and also something that I've been working on lately. And the topic of this talk is basically how to deal with a very extreme corner parameter space of a family of smooth microstate geometries, where it seems like something which initially did not have a horizon generally developed as horizon. Those of you who are familiar with the Fuzzball Proposal, you know that this is a no-go. What I'm going to present today gives a little bit of an introduction of how we try to attempt to resolve this issue. So the outline of the talk is to start with a brief introduction of the relevant key issues in the Fuzzball Proposal, and then introduce the limit, the singular limit that we're trying to work on. Next, I'm going to tell you really what's going on, what is the problem, what goes wrong when we take this go to this extreme corner of parameters, carries momentum in a new kind of way. And then finally, once we find the solution is described by a very particular set of BPS equations in 6-dimensional supergravity coupled to a additional vector multiplet. What we've done so recently is we linearize these BPS equations, which allows us to, in principle, construct super smooth solutions in this new frame as well. And a brief outlook of what is yet to come. So let's start with some basics. The first time we talk about black holes in undergraduate courses or in kindergarten, depending, usually associate some thermodynamic properties with them. And in particular, we know that we have to associate an entropy with them. Usually when we think about systems with entropy, we ask ourselves what are the corresponding microstates. And I hope this isn't a heretic statement to say that even though semi-classical geometry can give us a lot of information, we think that we should go beyond that theory to get some kind of resemblance of microstates, some explicit microstates. And one of the theories which should give us some insight of how to do this is string theory. And in fact, I think one of the main results from string theory is in fact that it can allow us to reproduce the Bekenstein-Hawking entropy by a nice counting argument. So these were, for example, for supersymmetric, this was done by Schromm, and so on. But also there are other proposals from which we hear later on in the afternoon by Horowitz and Ponchinsky, the correspondence point. Even though these kind of counting, all of these things still work some kind of in an ensemble way, right? The entropy of a black hole to an entropy of a large number of microscopic constituents. But then you still might ask, what are the individual? For the Fuzzball Proposal, it's important to have answered the question, what is the role of the horizon in all of these solutions? And I think there are two ways you can think about this, and I think we will hear about those two things today. The first one is you can think of, okay, let me start by weak coupling. I start with some fundamental string. It's kind of like it's as you coupling, it's wiggling around, and then increase the string coupling, it will start to attract, it will collapse, and at some point it can go behind the horizon, then the finite horizon forms. We'll think that, okay, all of these microstructure that you find at zero coupling, it's hidden behind a finite horizon. On the other hand, there's also been some results which say if you not just have some fundamental string, but also have some brain structure, if you have an additional D-brain in your system, when you start to increase the coupling, the brains become slightly more. If you especially on top of these brains, the brains start to expand as you increase the string coupling. And some results even show that when you increase the string coupling, actually the size of these microstructure goes exactly the same as the would-be horizon, but the horizon actually performs. So in kind of principle, this is the spirit of the Fuzzball Proposal, where you actually never really form a horizon. Is the horizon sets only the scale at which microstructures start to deviate from the standard black hole picture that we have. And it goes a little bit further. They exist e to the power as explicit microstates which have this non-trivial structure. So the picture that in mind is, oops, wrong button, is that instead of having a black hole structure, what we will have is everything up to really this near horizon limit where the horizon would be. You have everything exactly the same, but then you have some extra degrees of freedom coming from either string theory or any kind of UV complete theory, where it allows you to have non-trivial horizon, and this resolves a lot of the issues that in the formation paradox of entropy and so on and so forth. So of course, the typical state might include arbitrary high energy, might be very quantum and so on and so forth. But as is usual, there should be a classical limit consisting of really a coherent excitations of these quantum states, which should be visible in the classical theory, or should be at least well approximated by it. And these are the states which are visible in supergravity, the microstate geometries, which we've been talking about in the last few days, and will also be some the focus of the talk. Regardless, it's important to know that it's crucial that whether or not this solution should be described within gravity or not, all microstates should be horizons. So finding a horizon is really a problem. You might ask, okay, so how do we avoid the formation of a horizon? And is that you go beyond the GR and you have all of these extra degrees of freedom which allow you to support non-trivial structure at the horizon. And it's also, I'm going to stress, because this is going to be a problem for the next few slides, finite size horizons should only arise due to some average or some incomplete description of your theory. And again, stated in a different way, if you have a complete theory, if you believe you're in a complete theory, finite size should not correspond to any pure state of the theory. So obviously, I'm emphasizing this because this goes wrong. We found a counterexample. Naively, we found a counterexample. One of the most studied examples that we have is microstate geometries, which are smooth microstates of the extremal D1, D5P black hole. So this is still extremal. So everything I say will be in the realm of supersymmetry. So this is a limitation, but for a good reason, because then we have something explicit to work with. The family that I'm going to work on is called superstrata. And the nice thing about these, so these are black holes, which are microstates, which are asymptotically you have 4 large space-time dimensions. So this is 4,1 rather than 3,1 space. Then you have an extra, we single out this extra spatial circle, which will become important later. And then you have some four-dimensional internal manifold, which for concreteness we take T4 in this case. When you take the near horizon limit, as is usual, you will get the ADS 3 cross 3 instead of the R4,1 cross X. And this is in fact allows us to use ADS CFT duality. And this is very important because superstrata are a particular family which have a well-known CFT dual. So this allows us really to use the full strength of the ADS CFT duality to also get some results from, for example, holographic calculations. And because these states are supersymmetric, you can also use non-normalization theorems to match some results from the free orbifold point. So in particular, what these solutions look like. So you have the asymptotic region. I'm usually going to discard the asymptotic frat region. I should probably use the pointer here. And I'm with asymptotically ADS-free region. You have a long but finite size throat, which ends in a smooth cab because of a lot of microstructure. I'm actually going to focus on something that is called 1, n superstrata. These solutions are parameterized by 3 parameters. Of importance, I'm going to be only 2, which sort of are related to the charges that you can take in this theory. So B relates to how much momentum you have in the y direction in the S1 circle, whereas A essentially counts A here, small a essentially counts the number of momentum along the S3. And these two numbers are actually also important because in the holographic dictionary, which was established, is that these solutions are dual to a coherent superpositions of state. And these 2 states in the Ramon-Ramon sector are basically a bunch of plus-plus strands, plus-plus strands with winding 1. This is the same winding that Sean was talking about yesterday. These carry angular momentum, and the number of these basically determines these charges. Whereas you have, and these should be thought about as the background, as the super2 background in which we form these excitations. These kind of like add to the momentum. And in fact, what you should think about is, I'll make this picture slightly more precise, that these are excitations on the supertube, and L-1 is the usual Virasoro operator, which kind of acts as a boost along the XY direction. But okay, I gave you this limit, and in principle, these states are very well defined. So yes, sorry, one question. I think the redshift, so these parameters A and B also determine the length of the throat. So in particular, you see that basically the value of B, you can think of these kind of solutions as sort of ADS free, and then the value of B determines where you throw away, where you make a cut and just add a finite size ADS 2 cross S1 throat, and the length of which is determined basically by the value of A. So you can have the maximum redshift is determined by setting A as low as possible. And I think is determined, the redshift is sort of determined by, I think, by 8 times B, n times 8 times B, if I'm not mistaken. B over A, yes.
This is in string scale, in Planck scale, the Planck units, string units.
Oh.
No, I mean the A and B.
Oh.
So how far, if I was thinking about it as a horizon, how far this state extend beyond the would-be, or beyond its would-be, or
Infinite and zero. Infinite and zero. It's an external black hole, so the horizon of the external black hole is a little bit from the float, so it's a little distance. But then for possible or incoming observer, it depends how much time it takes for this observer. I think this is, so if you look at the distance and you measure the distance from this place to the horizon is infinite. It's an extremal black hole. The horizon of an infinite black hole has an infinite depth. So if you just integrate GRR from the horizon of an extremal black hole to here, you'll get infinite. But then if you look at an infalling observer, which falls in, then the infalling, and you ask how much proper time of the infalling observer takes from the moment it reaches this stuff to the moment it would go to pass through the horizon, then it's actually 1 over n1 and 5. It's microscopic. So the answer is infinite and zero. It's an extremal black hole. Very counterintuitive.
I guess I will have to ask it later.
Yeah. Yeah, but thank you for the question. It's actually quite important to know that basically, as you take A to 0, this length of the throat becomes longer and longer and it goes infinite, right? But I mean, if you have an extremal BTZ black hole, this throat is infinitely long, right? So it's kind of the question is kind of related to what I'm going to say next. In principle, I can assume A and B are not independent, but kind of like the cost of how many strands I have in the theory. So by increasing the amount of 0 strand that I have in this theory, I should again use the pointer, I should decrease the number of plus. And basically, by increasing B, kind of like, or by decreasing A, I can go into the space where the microstate geometry approximates the black hole more and more. And as long as A is sort of finite, this is fine. But in principle, nothing stops me from saying taking A goes to 0 strictly. The state I'm going to end up with is a perfectly well-defined CFT state, just consisting of 0, 0 strands. But on the dual side, what you find is A goes to 0 limit. In the geometry, you find just the extremal BTZ black hole. What it seems like, really, what we've been discussing before, that by taking A goes to 0 really strictly, what you find is a geometry with a finite size horizon, but the dual CFT is pure. So this is, for example, to the Fuzzball proposal. So now you have to figure out, so what goes wrong? The question that we want to ask, that we want to answer here is, can this horizon be resolved with gravity? Are there any real momentum carriers which allow us to describe the system even in this particular limit? Yes. I think I think it stabilizes at a different value. So you have the, and then it stabilizes at some other point. I don't know the precise value.
Nejc.
The momentum charge determines the radius of the throat. And here the momentum charge is set by B squared.
Yeah, sorry.
Emil.
So maybe to answer both that question and Rami's question. So you really have to ask, when you're talking about redshifts and so on, relative to what scale. So let's fix a scale. And a nice scale to fix is the place where the left of the figure, which is asymptotically ADS3, transitions to some region which is looking like ADS2 cross S1. Okay, so what's the S1? The S1 is the angular part of ADS3, the azimuthal circle of ADS3. So that's something which is decreasing exponentially as you come in radially. Eventually it hits some scale. What scale? The scale that's set by the momentum on that circle, which is QP. So that's the scale B, or root n times B, that's on the figure. And now you transition from an ADS3 region where that circle is exponentially shrinking to one where it's fixed radius determined by QP. Okay, so now you descend for some time in redshift, a while in redshift, until you get to the scale set by A. A is the angular momentum that's carried by the solution. And at that point, the geometry stops being ADS2 times S1, and that azimuthal circle starts shrinking again. And so you have this cap region, which looks locally like ADS3 again, until you reach the center of space and space ends. Okay, so the interesting thing here is to say, okay, let's fix QP, and now let's dial the angular momentum. By dialing the angular momentum, you dial the scale A, and you make the redshift either longer or shorter. And he wants to take the limit A goes to 0, i.e. turning off all the angular momentum, at which point gravity says that the cap should become infinitely redshifted and go to some extremal singular geometry. And so he wants to ask the question, if I understand correctly, what do you do to patch up this sort of fact that the cap has descended in? Is there anything that's sitting in the cap that prevents it from going to infinite redshift? What's at the scale of that?
Cool. Thank you very much. Yeah, this is precisely it. Emil is precisely right. This is what I forgot. When you take throat, and this throat is finitely long, and then you have this another free region, this smooth cap here. The question why we want to resolve this in supergravity is also very important, because we know from the two-charge case, which were described by Kanishad, Skenderis, and Taylor a while ago, that these states, when you take the A goes to 0, you work with singlets of the symmetry. And what we know is that in the two-charge case, these cannot be described within supergravity, or they argue this is not described within supergravity. Unfortunately, these are also very interesting, because if you manage to find microstates with would-be singlets, these in the same paper, they made an argument that these will give a very huge entropy towards counting. So, there are several interesting motivations why we want to be this kind of limit. But before we go into that region, I want to describe why just from the and this is just the standard picture of how you construct these superstrata. You start with something which is called around D5 supertube, and you by having a supertube with non-zero is A, and A is precisely the space which determines the number of plus strands of geometry. The next thing that you do is you add along the radius of the supertube something the excitation. We single mode excitation of mode K, and this K essentially the dictionary determines the winding that you have. This is again the winding that we talked about yesterday, and the amplitude of this is called we denote by B, and determines the number of 0, 0 strands that you turn in the geometry. When this is small, it's just sort of a perturbation along the supertube radius, but when it's large, we have finite back direction, we get this kind of geometry. The final step that you want to do, so this kind of this geometry, when you have the excitation, there's no excitation along the y direction, along this y, along which is common direction of the D1, D5 branes. But when you act with the L-1 generators, and these kind of act as a boost along the y direction, and these then give you momentum. And the amount of time you act with generators on this solution gives you the amount of wiggle. So in the end, you kind of have a doubly wiggling supertube. And once you back react this, what you get is your geometry that you discussed. But now, if you think about this, when you say A goes to 0, what will happen? You decrease the circle along which you put your excitations in. So in principle, what you're asking is, okay, I'm going to decrease the circle And along the circumference of the circle, I'm going to put an excitation. So of course, this is an ill-defined limit, because what you're doing is you're suppressing all the oscillations, the possible direction on which you can put oscillations. By taking the a goes to 0 limit, keeping is its effect. You're keeping the RMS value. So in effect, what you're doing is you're throwing away all of your momentum carriers while still keeping their effect. So the way it's saying, we're steering over the degrees of freedom which can actually carry the momentum, also keeping the result itself. If you think this more from the gravitational side, connect to what I was saying yesterday, if you back supertube and I think the origin, there is this cycle in which you have this flux. And when you take it goes to 0, this free sphere goes to 0, and then you kind of like again the effect is the same. The fluxes which carry the momentum has nowhere to be, but you still keep their. So, how do we resolve this? The goal is to find, can we find some momentum carriers which have vanishing angular momentum, so something which doesn't expand in the R4. And the best way to think about it, there's actually two ways of doing so. The first one is you need to either involve the 4 degrees of freedom, so the degrees of freedom which oscillate along the internal direction, or you want some excitations which are actually longitudinal S1 circle. So these are some excitations which don't extend in the R4, but oscillate along the SY circle. And these will essentially go into choose the second option, precisely because then we don't have to involve the T4. So we the internal manifold. And it turns out the best frame is actually type 2A frame. There you work with actually the S and T dual of the D1, D5P black hole, work with the E1 and S5P black hole, and then you find that momentum can be carried by two D4 charges. So what you do, this T4, you wrap D4 brains, and then you have D0, which is smear along this manifold as well. But then you add some local non-trivial density on the S1 circle. If you're perhaps if this sounds a little bit weird, think in the if you uplift to M2, which just wrap the additional direction, but this trivial profile, this non-trivial longitudinal directions, actually combine with the NS5 to get a wiggling M5. So you get a non-zero, non-trivial M5 profile, and this profile of the F5, well, FV, now this down to give you this longitudinal profile, these excitations. So how do we do this? How do we do this? Well, we're in Saclay. What we do a lot of dualities. So what we're going to do is we're going to start with the fundamental string, which was this, which we know the the supergravity solution of by works from these authors. And what we're going to do, we're going to along the one direction. This is going to be the winding direction. Add a non-trivial excitation, a non-trivial profile along one of the directions. So initially, we start with the system which inherently breaks in terms of the T. But then we can do a bunch of T dualities to make it something which is T4 variant. The fun thing that we want to do, if our goal is really to have something which has non-trivial excitation, non-trivial profile along the Y circle, we're not allowed to do a T duality along this circle because then it will take us out of the regime of gravity. So chain of dualities we do is this. It's actually not important. The details are that important. The important thing is we start with the fundamental string, which has a non-trivial below the line are always the dipolar charges, which integrate to 0 when you integrate over the Y. And once you do all of these dualities, what you find is in the end, you have an NS5 brane with momentum. This momentum is carried by D0, D4 charges. So start with some kind of asymmetry in the T4 directions, and you undo them by choosing this preferential direction when you do the T dualities. And the final thing that we want to do is, because this configuration is still supersymmetric, we can use this enhanced supersymmetry. And the ansatz, we know how to work with supersymmetry by now very, very nice. We can use this additional supersymmetry to just slap an additional fundamental string charge on top of it. So what we do is we have an NS5 brane, which is has this 0d4 charge, and we add very static F1 brane smeared along the T4. Just to give some examples, you can show that this configurations preserve locally 8 supercharges because because these modes are very specifically tuned, coming from the fundamental string. Globally, because of this, we preserve 4 supercharges. So the same amount of supercharges as the D1, D5 black hole, but low looks like a 2-charge black hole. This will become, and we will see this appear later on explained. So this is the money shot of this presentation. What we find, okay, so we're describing this configuration at the top, and in terms of the string frame metric, and in terms of the Ramon field and gauge fields, this is the solution. You see that in most cases, it looks exactly what you would expect from the F1 and F1 S5P. The only addition that you have is you see there's an additional, there are additional terms which explicitly depend on this profile. And in fact, they depend on F dot. What's interesting is, we started with something which is localized at a point in the R4, but you can see that all of the functions which are proportional to F dot, they have this weird factor 1 minus 1 over H5. So this is something weird. It's not localized at a point. It's actually like it has a peak, and this will become important later. It's kind of weird that you find something which you started with a configuration which is everything is localized at a single point in R4, but what you get something which is effectively smeared along the direction, the R direction. And still, you can do the asymptotic analysis, and you find that the momentum is given by just the 0 modes of this distribution. So okay, let us. The important thing is, so what happens near the brains? So the first thing that you think you can look at is you find that there is a horizon R is equal to 0. So this is still a singular solution. But actually, despite being a solution, what you find is that the horizon area vanishes. So this happens because now you have basically you can show that the radius of the Y circle now, instead of stabilizing finite value, which is determined by this asymptotic momentum, actually pinches off at R is equal to 0. So this kind of goes against the standard picture that we have when we talk about black holes, where the R is equal to 0, you have an equilibrium between the tension of branes and the pressure exerted by the momentum charge. And in fact, one could go a little bit further by taking the near horizon limit, and you find that basically it's essentially empty ADS3 cross S3. The only additional thing that you can do is you have a non-trivial deformation of the metric, which is determined by F of V. All the other ones, so this ADS cross structure is supported by the NS flux, but all the Ramon charges are basically vanishing. So to kind of explain this, one can plot the V function. So this the metric somehow determines the momentum, not of the AD3 structure, but from the complete solution, and you can compare it to the black hole. And what you find is comparatively, the red line here determines the black hole. Instead of having something which really which has a peak at R is equal to 0, corresponding really to a point-like source, what you find is that the distribution here is slightly more moderate, and it's actually seems to be expanded. And when you analyze it a little bit further, what you find is that the peak is actually of the similar radius to ADS. So instead of something which has a localized point source for the momentum at R is equal to 0, you find basically a 2-charge solution which has a null momentum wave running around at some finite distance, which is actually at the transition region. So in terms of that, it shouldn't be surprising that basically the near horizon limit just captures this initial R squared growth. And it's actually quite important is to see that you actually, when you take the near horizon limit, you don't get the full details of the solution. You actually, you kind of, when taking it, you throw away the entire bump. You throw away the details of the momentum carriers are. And if you, okay, so just alternative way of how to see this, if you're unfamiliar with the D0, D4 charges, one of the things to think about is that you can reverse the chain of dualities that you started from F1P to the final frame after you added this fundamental string, and you find that this final frame, you actually end up with an NSP F1 black hole, but now the momentum is carried by literally the same F1 strings with momentum along P4. So in the end, you can see that what we're doing now essentially is we are with this D0, D4 charges, we're essentially probing the along the internal direction. So yeah, if you look at perhaps another way of seeing this, if you're familiar with the D1, D5P system, if you look at this D0 to 4 momentum carriers really include the T4 degrees of freedom of the D1, D5 system. However, from the 6-dimensional point of view, this solution and the solution that I talked about before are actually kind of the same. In fact, actually down to 6 dimensions, you will find that because of this additional factor in the metric, you get an additional gauge field. So from the 6-dimensional point of view, the only thing that your system is described by supergravity with an additional vector. Still, the solution that we described so far, this is still a singular solution, and in order to get something which is smooth, we will have to use the we will have to solve the full equations of motion. We have to solve the BPS equations, and if it leads us to the final thing, we need to solve the BPS equations relevant system for 1, 0 supergravity with coupled to a tensor and a vector multiplet. Luckily for us, these solutions have been described before in the literature. However, the equations are slightly unruly. But what you can find, similar to what has been done before with systems which only involve tensor multiplets, is that these solutions, these BPS equations, can be appropriately linearized. And you can write encompasses the string theory origins of the solution. And in fact, this is the complete answer you can think of. This is the new H field completed with the 2 B fields. B field had a tensor field. Have a tensor field coming from a gravity multiplet, a tensor field from a tensor multiplet. So in the end, the free form is unconstrained anymore. So it's appropriate, it's sort of convenient to write in an independent way. And to think about this in a natural way, you see that if you think about the F1 and S5P solution, T0 to 4 brane charges, the Z1s corresponds to the sources, vector sources of the fundamental strings. The Z5 correspond to the sources of the F for momentum and Z for D0, D4. And it turns out that once you work a little bit with these equations, that the ZA, which is the dV component of the vector field, kind of naturally appears also in the momentum function here. So in the GVV component. And it's important to see in our conventions, F is usually negative, whereas Z squared is fundamentally positive. So there will be 2 competing contributions like this, where one will come directly from the momentum charges, and then the opposite effect from from vector field. Okay. Most horrible slide of this. I just wanted to flash all of these equations here. The details of it, the complete details are not important. I also simplified them slightly because it's not important. That I want to show you these again separate into a nice layered structure. What you see is for people familiar with the D1, D5 system, you again have a layered structure now, but now this additional vector field introduces a symmetry between your tensor field multiplets. So the first layer on the top, I've already fixed the base space. The first layer is exactly the same as the previous system. The second layer, it turns out that once you solve for theta 1 and Z2, you can go for the next layer, which is just, again, a self-duality condition for DA and actually a generalized Laplace equation for ZA. And once you have these solutions, only then you can go and solve the next tensor field equation, which determines theta 2 and Z1. Usually, people who've been familiar with the D1, D5 system, tensor field equations are basically decoupled and you can solve them simultaneously. A nice pictorial way of you can think about this heuristically is that Z2 and theta 1 correspond to NS5 branes, which are sort of the heaviest. So therefore, you have to solve them first. DA and Z4 correspond to D0 4 charges, which are slightly lighter. So then you have to, and you have to, and finally you solve for the most light elements of your string, which are the fundamental strings. Last layer, you just need to solve. Back reaction of your solution. Most important thing of this is that here, nice to solve. In particular, we have a structure that once you have a layer, the next layer can be solved in principle. You have only quadratic sources. The same principle that we've been used that allowed us to construct all of these smooth solutions in the previous are also And as I mentioned before, this vector field introduces a weird asymmetry between those two tensor multiples. Before I finish off, let me try to tell you what how to use this solution to analyze the solution that we had previously. So as the dictionary is, we mentioned that the dictionary is as such, and I can use the solution for brane charges and put them in. I found, interestingly enough, even though I said that the functions which are related to the D0, D4 charges do not look harmonic, once you actually analyze it, you find that all of these Z functions which appear in the ansatz and all of the F functions are actually harmonic, and they actually correspond to point sources in the space. What is going on is, in fact, if you remember that in the GVV, in the dV squared component of the metric, we have this particular combination. And when you take the near brane limit, actually the leading contributions cancel out. And they cancel out precisely. Then related to this quadratic increase right near to the analyze this to just further illustrate this point. Once you put background in, once you realize the PS equation you have to solve are just Laplacian equations in 4 dimensions, solved by R1 over R squared solutions. Instead of having these general V-dependent terms, I can just cook up an example where I put the QA and QP as constants. Okay, so this is a very artificial example, and now the no interpretation, the system now reduces by dimension as well because there's no V dependence. But what you can do is then you can just plug this into the equation and look with your solution. It turns out that the first thing you notice, you start to look at, and you find that R is equal to 0. This length is determined by quadratic combination, which shouldn't be surprising from some results in terms of 5-dimensional black holes, that this quadratic invariant comes up. But the one thing that you notice is if I want to avoid closed timeline curves, if I want the GV, the length of the Y circle, I want the square of A to be bounded by this number. Okay, so if that is the case, let me analyze what happens. Increase the amount of U1 charge. So standard F1 minus phi3 black hole. I just start to increase the Q1 field, QA charge. On the left, you will see you have the same GVV plot that we had before, and you see red corresponds to the black hole, and as you increase the QA charge, you see that this this kind of low price, the momentum starts to decrease, and it goes closer and closer to our solution, which in fact is saturates this bound by it's sort of like in a slightly more complicated way. Another way of seeing this perhaps is to look at a similar to something to a plot which determines the length of the Y circle, the radius of the Y circle, and you can show that there are in general the regions. The first one corresponds very far away, which is the asymptotic flat region where the circle is stable at a constant radius, which for normalization reasons I take to be 1. And as we talked before, there's close region, which is where this R circle, this is where this R circle starts to drop. And then at some point, at some scale, which is the QA charge, you transition back to the ADS2 throat. But you notice that if I saturate this bound, which is exactly what happens for our solution, you will get this you will have no ADS2 cross S1 throat. And the physical interpretation of this is that these momentum charge carriers we introduce have sort of a dual role. I think of this sound waves, sound longitudinal waves. So the first contribution comes from just having momentum, which comes from the charges. But on the other hand, you have that these charges source a U1 field, which kind of acts in the opposite direction. So they kind of, these two things cancel out. That they want to, and in our solution, which comes from string field, these two effects precisely cancel out at I0. Okay. So just to summarize what we have done, we have analyzed the singular limit of superstrata, where when we look at the solution, we had a size horizon in a very particular limit. and which is dual to a pure state, and we analyze what is the cause of this appearance, what happens from the construction side point of view. We showed there exist explicit solutions. What we analyze right now, we have asymptotically free charges, but these solutions, even though they correspond to holes which have a finite size horizon, do not develop a finite size horizon. And the key ingredient for doing so is identifying new degrees of freedom which do not expand in the R4. So these are singlets under the R4 space. We found some interesting solutions because of this absence horizon is due to this non-trivial cancellation of field contributions to momentum and its opposite direction. But one of the things that's sort of puzzling is that when you take the near, though you have some kind of structure, the near horizon limit seems to be empty. And we showed that in the BPS system of equations have a vector field. So have we solved the problem? I'm at least skeptical in saying not yet. Obviously, we identified a mechanism which prevents the large size horizon. In principle, what we would like to do is we would like to move solution in this frame. We would like to then see if the same mechanism can prevent the formation of any side of horizon. So now we have zero size horizon. There is still a horizon which has zero area. But in principle, what we want to do is we want to find some big solutions, take goes to zero limit, and find whether the horizon is or not. One of the things that we've been trying to do in the couple of weeks, in the last couple of weeks, and we haven't done any significant progress to show this. Well, one thing that might actually be the case is that this empty near horizon region is rather a feature rather than a bug. So it might be that these solutions fundamentally live on the boundary. Okay, this, as the title of this frame says, these are wild speculations. So this is not based on, this might not be true. But it would be interesting to see if we manage to do so. What is the holographic interpretation of this? These states should be in principle BPS, so we should have some kind of, they should counterpart in a CFT if they're supersymmetric, visible in the orbifold point. And perhaps one of the ideas might be, can we make some holographic in the CFT, which might point us towards some explanation, which might give us some hint. Another which kind of crystallizes when we do so, when we do these calculations, we see that T0, D4 modes can be related to T4 degrees of freedom. So now there's the question, how important is the internal manifold in all these calculations? So far, the super sort of the microstates that we built have been built on sort of like a universal sector, which depend on the choice of the internal manifold. And now the question is, how much is the internal manifold important in general when you construct these solutions? And for what we saw yesterday from Kerr Stock, that the internal degrees of freedom, this internal structure is quite important to allow for some non-trivial structure of the horizon, some condition. Perhaps the question is the resolution fundamentally stringy in nature? Perhaps we have to go beyond supergravity to fully resolve this issue. And this might be related to work which might be described by Emil or David and Nico in the following weeks, following days. Perhaps on a slightly more question is, can we make this system that we described for the linear for the limitation of just one vector field to general vector and tensor field, which allows to have a much richer structure. This system was studied by Kano and Ortin, but I think the linearization might really depend heavily on the choices of couplings between the tensor and the vector multiplets. And perhaps interestingly would be to analyze this linearity to other be supersymmetric, relates supersymmetric systems, non-supersymmetric systems. And I think that should be it. Thank you very much.
Let me start from Daniel, then I come to you.
Thanks. Yeah. So can I? So in the D1, D5, the two-charge system, you have these. Well, you have the Luna Mathura supertubes, which have an extension in the non-compact space. But then you also, if you want to like count the complete entropy, you also take into account guys that are sort of singular again in the non-compact space, but have like a profile on the T4.
Yeah.
So so can I sort of think of your guys as the a three charge generalization of this idea?
I think so. Yeah, that's how I
Right.
would think about this, right? I mean, ideally, this would right now what we've done is you have this, you have basically the one part of it is similar to Lunin Matur, but then you would have to add this this additional charge, which I don't know whether Lunin Matur can do. Right. But I think, yeah, I think the answer is yes.
Okay.
I think that there would be some kind of generalization towards this to have, you know, non-trivial structure, non-trivial profiles along the T4.
Right, exactly. And so then for sure the internal manifold will be important. I mean, there you know from you know the Lunin Mathur thing, it depends on what you have, a T4 or K3, and then and then it depends. And so do you have any expectation on, like, there, you know, you count the guys in the non-compact space, you get some finite fraction of the entropy. You count the guys on the compact space, you get another finite fraction. But they're both sort of the same order. Here, I don't know. Do you have any?
Yeah, unfortunately, no. Unfortunately, no. I wouldn't.
It's a bit different though, because here the degrees of freedom are actually M-theory degrees of freedom. It's okay, I have one. Then the degrees of freedom are actually M-theory degrees of freedom. So if you look at this 0 D4, you know, you are not having anything on the internal manifold. The internal T4 is still frozen. There's nothing happening there. So these degrees of freedom actually, they correspond to fluctuations, but they don't involve the T4. They involve the M-theory direction. It's a different flavor.
So
because
you're not yeah, okay. But
so
but I
the
guess
T4
you
is still
want to
frozen
generalize
here.
this to also
yeah, you can
fluctuate
dualize
the
this to
D4.
the other one, right? But you
No. You cannot dualize the D1, the F1 and S5P frame with D0, D4 fluctuations to the 2B frame we have. No.
Yeah, okay, no, not.
I mean, if as three charge solutions, I don't think you can dualize them at all, because, you know, you're basically, I mean, they depend on the V direction. So normally you dualize on V to go from the type 2A frame to the type 2B frame. Can you throw it in the? Oh, throw it. He's too British.
These things can also in the sort of in the M theory frame, and then really what you're doing is you're doing something on the M theory circle, but then that's like a T5 compactification of M theory. You could move the thing into the T4, I think, Joseph, and at which point you're now doing a T4. It's a mode on the torus of the T4. So I think there is probably a perfectly decent ADS CFT interpretation in terms of excitations on the T4, and you can do that in 2A or 2B. The only reason we did it this way is because it's much easier to freeze out all the T4 degrees of freedom just through the supergravity analysis. And so it gives you this nice picture. But I think in principle, this is just activating the T4 degrees of freedom in a new and interesting way. And it's qualitatively, as you saw, because it delocalizes, it's qualitatively rather different from what we've seen before.
So do I understand correctly that the reason that things become trivial when you try to take an ADS3 decoupling limit is that the D0, D4 excitation is carried sort of outside the ADS3 region?
Yeah, this seems to be the thing that we know. Once you include the back action, it seems that the where this momentum wave is localized is sort of at the boundary region between the ADS and the flat space in this transition region.
So follow-up question then. So it's sometimes interesting to try to separate to stage a hierarchy of decoupling limits. So instead of going directly from flat space to ADS, you can take a hierarchy of decoupling limits where, and especially since you have your backgrounds NS5s, to take an NS5 decoupling limit first. So try to erase the 1 in the 5 brane harmonic function, keeping everything else.
Yeah.
Have you looked at that?
We have tried it, but I don't remember the result. But I think that's a possible way forward, where you start with just the normal decoupling, the NS5 decoupling limits first. And that might be a way forward, rather than looking directly into the ADS3 limit to go into that frame. That decoupling might be slightly forward, but I don't remember the result.
I don't think it works. I think we tried. We would have made a big noise if it worked. We tried and it didn't work.
So it's even carried outside the 5 brane throat?
Yes, I think so. If you take the 5 brane, it's the 5 brane harmonic function, which is really the bad one.
Possibly how it touches on the flat space. It seems very odd.
Ah, but actually, Actually, I have to take it back. We have one solution, which is not the one with the 0D4, but which involves F1P.
Yeah.
And that one, I think we can take the NS5 decoupling limit. That's a very good question. I think we can have one which goes inside the NS5 region.
Yeah, so this one, right? So this one, when you do this calculation here, so have I made it? No, I have not.
No, it's the other uplift. It's the one we've been discussing recently, the one with F1P on the torus.
Yeah, that's the one. That's the one here.
Yes.
That's the one here. Here you notice that here actually when you do this dualities, the the H5 and the H5 and H1 get changed. So H5, which appears in this function here, is now actually corresponds to H1s. So, yeah.
Thanks. That's very useful actually.
Yeah.
So in this background that you have in front of us, so if you set f dot to 0, you get the pure NS5 F1 system, right? F dot to 1.
If you take f dot to a constant, and yeah.
Okay. So in that case, the theory on a single long string will be something like R5 is a Liouville type, and then SU2 times T4. Now when you turn on this f dot, the T4 is no longer a straight line. So do you have any idea what the theory around single long string is going to look like?
Unfortunately, no, that is out of, I mean, I know that people have been working on this, but that is out of my expertise, unfortunately. No, but this is a very important question because the reason why we use this this background because early NSNS, right? So this might be interesting for other purposes, but unfortunately that is out of my.
But what would be the theory, the free theory, the orbifold theory in the other frame? Like it was T4 to the power n mod Sn kind of thing before you add the f dot.
Yeah.
So now what's going to be the orbifold theory?
Should be the same, right?
I'd
say it's the same. It's just the same asymptotics. It's just the same. I mean, the type 2 and the type 2b F1 and S5 system, they are part of the same. They have the same CFT dual. I mean, the Furby fold is dual to everybody and their brother. You know, D1, D5, F1 and S5 in type 2, F1 and S5 in type 2b. All the dualities are just moving around amongst supergravity theories, but there's a single Furby fold point. So I think it's the same. It's the same Furby fold theory, but it's just dual to all of these guys. So those guys are going to describe some states of the Furby fold CFT, but you know, which don't have a type 2b clean interpretation. So.
Another way, I mean, you know, the things that we've tended to use to build superstrata carry our symmetry. That's what makes them fat in the space-time. They have a leg that sticks, the polarization tensors tend to have a leg that sticks out in the space-time. So the particular charge carriers we're using here, or the particular dual states, are things that are entirely internal to the system and don't carry any R symmetry. That's why they have their SO4 singlets. And so that's what makes them, you know, qualitatively different, and I think probably very interesting.
Monica,
okay, yeah, maybe I just want to add one point on this. I mean, but if they don't carry any R symmetry charge, how can they be BPS, right?
They are.
I mean, usually from the CFT point of view, I think a BPS condition being H equals J. Right, but it's the J of the S3, right? Usually, I mean, another thing which makes me suspect that you need to go beyond supergravity is when you describe the superstratum states, right? As you said, that these are coherent superposition. So you have two ingredients, but you don't have fixed number, right? You have a coherent superposition, and this number, the average number of the constituents has to be large.
Yeah.
Right. When you take A equal to 0 limit, you don't have a coherent superposition anymore, right?
Yeah.
You have just a state. So I had the naive suspicion that then you driven to a stringy state.
Yeah.
I think I can answer that. It's possible. So it's possible. Notice that this solution still has a horizon. It's still singular, but the horizon area is 0. So it's an improvement. Now, if you want to make a microstate geometry out of this, you might actually have to once again reinvade the space-time and make it big and fat. But the nice thing about these momentum carriers is when you take the A goes to 0 limit, you don't wind up with something with a finite size horizon. You wind up with something with a 0 size horizon, which means its resolution must be intrinsically stringy. So I think that's how this is probably going to work.
Monica had a question. Monica had a question.
Okay. More questions? Okay, then there are no more questions, let's thank Nejc.